Hello, everyone. I'm Jen. I'm going to present our work on type-directed program synthesis for REST APIs. Consider that you are given this real problem from Stack Overflow. In this post, a user is asking about how to retrieve all member emails from a Slack channel. The desired solution includes the following steps. It first calls conversations list to get an array of channels. Then it finds the channel in the array by the provided channel name. Next, it calls conversations members to get all member IDs in the channel. For each member ID, it calls conversations info to retrieve the corresponding user object. And finally, it accesses member emails by field projections. As we can see in this program, there are 3 method calls, maps, and filters. So it is challenging for a user to come up with in a short time if the user is not very familiar with the method definitions and object definitions. So can we let a synthesizer automatically find such a program for us? In program synthesis, a user usually needs to give some kind of specification and some components to the synthesizer. Then the synthesizer searches for programs that satisfy the given specification. So if we want to use the synthesizer to solve the task from our running example, the first thing we need to figure out is how to express the intent to the synthesizer. In other words, what are good specifications for the REST API domain? The most common specification used in program synthesis is example. When we try to write examples for REST APIs, we find 2 problems with it. First, many methods have side effects, like creating or deleting resources, which means a previous execution of a program may invalidate the provided examples. Second, a lot of methods work with large JSON objects, and writing down these complicated objects as examples is almost impossible. So we think examples are not good specifications here. Another common spec is natural language. We try our running example on GitHub Copilot, but GitHub Copilot is a program synthesizer that takes natural language description as input. But Copilot cannot solve the problem at all. It generates programs that tries to call some non-existing method. So this indicates that natural language might be too vague to describe the task in the REST API domain. Therefore, we think natural language does not fit here either. Recent work on type-directed program synthesis has shown the power of types as specifications. Does it work for REST APIs? There have been type definitions in the standard documentation for REST APIs called OpenAPI spec, but most of the types defined in OpenAPI spec are strings. For example, look at this method, conversations members from our running example. This method is supposed to take a channel ID and returns an array of user IDs, but its OpenAPI spec definition is very coarse-grained. It just says this method takes a string and returns an array of strings. And this is so typical of the REST APIs that they are often referred to as stringly typed. So in this work, instead of using string types, we introduced the more fine-grained type called semantic types for the purpose of program synthesis. And we built a tool called Epiphany that helps user infer semantic types for methods and generate programs from them. In detail, our first contribution is a semantic type mining algorithm. The algorithm is divided into 2 parts. In the first part, we take the OpenAPI spec and try to construct a semantic type from it. In the second part, we collect execution traces by observing the traffic from the API's web interfaces and random testing, and then use these execution traces to infer semantic types from methods. Once we have semantic types, we call a type-directed program synthesizer on some type query, also written in semantic types, to generate programs. But soon we find that although semantic types are more fine-grained than string types, they are still ambiguous. We get hundreds of programs from the synthesizer. So our second contribution is a ranking technique called retrospective execution, which ranks meaningful programs higher in the result list. Now, let me introduce how we construct semantic types first. Suppose we want to write a type query for this task from our running example. It would be nice if we can say something like channel name to array of user emails. But how do we represent such semantic types so that the synthesizer understands what we mean? Our insight here is that we can represent semantic types using the information of object structures from the OpenAPI spec. For example, the Slack spec, API spec contains the descriptions of objects such as user, profile, and channel. Then we use the object and field names to represent semantic types. For example, the semantic type for user IDs is written as user.id. Using this scheme, we can assign semantic types to all object fields that were previously annotated with strings. And with this representation, a user can now express the intent as a semantic query, channel.name to array of profile.email. After we know how to represent semantic types, let's see how semantic types are inferred for methods. The left part of the slides are the semantic types we constructed. And on the right are the stringy typed method signatures from the OpenAPI spec. The goal of semantic type inference for methods is to replace the strings on the right with the semantic types on the left. How to achieve that? Here comes our second insight. We may mine semantic types for methods from their execution traces. On the left, I show you an invocation trace for the method user's info, and on the right is its spec type from the OpenAPI spec. And now I am going to show you how we infer the semantic type for user's info with the entry on the left. First, according to the spec type of user's info, we know that this method returns a user object. Therefore, the ID field of the return object can be assigned the semantic type user.id. Meanwhile, we find the same string value appears as the argument of this method call, and we have known that this string value has semantic type user.id. Combining these together, we may say that the argument of user's info has semantic type user.id. By applying this process for different invocation traces we have collected, we are able to get the semantic types for all methods on the right. Are we done? Not yet. Recall that we assigned a unique type to each string field of each object previously, but some of these fields intuitively may belong to the same semantic type. For example, consider the creator field of the channel object. We have assigned it a unique semantic type channel.creator, but in reality, this field stores user IDs. So to get more accurate semantic types, we need to merge these two types into one. Again, we turn to the execution traces to get such information. Suppose from some part of the traces, we get a channel object on the left. With a closer look, we can find that the creator field of this object is the string value we have seen before, and we already know that it has semantic type user.id. Therefore, we successfully infer that the creator field of the channel object has semantic type user.id. Put all these inferred information together, we get a semantic library where all object fields and methods are annotated with semantic types. With the semantic library on hand, we use an existing type-driven program synthesizer with a minor modification to generate maps and filters as in our running example. In this talk, I'm not going to introduce the details of this part. If you are curious, please check our paper. The next challenge we're faced with is that the synthesizer produces hundreds of programs for a given type query. So we need to rank these programs in such a way that the user only needs to inspect a few top-ranked programs to hopefully find the program they are looking for. To implement such a ranking algorithm, we propose a new technique called retrospective execution. Let's see why ranking is difficult for REST APIs and how retrospective execution overcomes these difficulties. Recall that this is our desired solution. Suppose we have two other candidates that are different from it in some small places. Our candidate 1 returns the email of a channel creator instead of all member emails. Intuitively, we can determine that this program is less desirable by observing its behavior and noticing that it always returns a singleton array rather than the expected array of many elements. Candidate 2 calls conversations open in the first step, but this program is also less likely to be the solution that a user wants, because at least one optional argument has to be provided to successfully call conversations open. Otherwise, it would always fail during execution. The question is, if we get these three problems from the synthesizer, how can we prioritize the desired solution among the three? A straightforward idea is to run these programs and then rank them according to the execution results. However, program execution in REST APIs is not easy. The service providers usually set a rate limit on how often or how many method calls one can make, so we cannot execute these programs as many times as we want. Apart from that, many APIs have side effects, and we cannot restart the server from a clean state for each execution. So instead of executing these programs directly, we propose to replay method calls with their execution traces. Suppose we want to execute these two lines from some candidate program, which contains two different method calls. Because of the difficulties we just mentioned, we don't want to invoke these methods directly. But remember that we have a large database of execution traces, which contains several successful invocations of these methods with different input and outputs. Here we depict the inputs and outputs of method invocations as colorful shapes. The shape means their semantic type, and different colors means different values. When we try to execute the first API call, we simply pick an invocation entry of the same method from the traces. Assume we pick this second one and get this green triangle as the output. Now it's time to execute the second method call in the program. Luckily, there is an entry for this method in the traces that takes a green triangle as the input. So we pick that entry to simulate the second method call. In this example, we obtained an exact execution result by replaying a sequence of method calls from their previous executions. But things do not always line up so nicely. Let's come back to the first method call and assume that we picked the first entry as the simulation, and we get a yellow triangle as the output. When it's time to execute the second call, we don't have an entry in the traces that takes a yellow triangle. Instead of giving up, retrospective execution will still use the entry with green triangle, so it effectively stitches together multiple previous executions to make up a new program execution. Although the result of such an execution does not match precisely with that of an actual execution, we find that such approximate results are good enough for ranking purposes. So we use the results of retrospective execution to assign scores to the programs and then rank them by scores to produce a ranked list. These are our main contributions in Epiphany. We evaluated Epiphany on 3 real-world APIs by collecting 32 benchmarks from Stack Overflow and GitHub. These benchmarks include tasks like our running example that makes several method calls and retrieve information from the web server. They also include effectful benchmarks like delete the payment source for a customer, which requires the program to call methods that modifies the server state. Epiphany is able to find the desired solution for 29 out of 32 benchmarks within the 150-second timeout. To further understand the effectiveness of semantic types, we compare the performance on semantic types and types from the OpenAPI spec. It turns out that with spec types, the synthesizer can only solve 4 benchmarks, and these benchmarks are relatively easy. We also compare the rank of desired solutions before and after retrospective execution. Before RE, the solutions come in the order of sizes, and only 12 benchmarks have their desired solutions ranked in top 10. Even worse, some of them have ranked lower than 1,000. In contrast, after RE, 23 benchmarks have their desired solutions ranked in top 10. This shows that RE successfully improves the rank of the desired solutions. That's all I want to talk about Epiphany. Thank you.
I like this idea of semantic types, which actually reminds me of one of the standard ways of representing APIs in the ML family of languages, in the sense of OCaml, not machine learning, where you just have abstract types for each of these categories. So this almost sounds like inferring the kind of APIs that, say, OCaml programmers would already write manually for web APIs. But it almost seems like it's too easy for you, in the sense that in some cases you're relying on the disjointness of the possible value sets for different types, which doesn't sound like a realistic assumption. Like maybe social security numbers and phone numbers overlap, and if you happen to see the same number for both, then you totally make the wrong decision. Does that issue show up in practice for your tool?
Right. We do witness some overlap between values of different semantic types. Like we see the overlap between channel name and usernames, but that does not prevent us from finding the desired solution. We just spuriously merge these 2 types into one. We can still use our type-directed program synthesis to find programs. It just introduced some spurious programs that, for example, use channel name as the username somewhere. But we can still find it. It's, the algorithm is sound, but it might be slower because of these spurious programs.
Thank you.
Thanks for the talk. So in the, it seems like your algorithm uses sort of traces at several points. So I was just wondering sort of, where do you get these traces? How dependent is the algorithm on like the quality of the traces? How easy is it for a user to accumulate kind of these traces of API calls?
In our experiment, we collect the traces from their web interfaces. So the 3 benchmarks we picked all have some front-end web interfaces for us to use. And we observe the traffic through the Google Chrome and collect the hard file from it. And we also do some random testing by execute all the methods in the API spec.
What about side effects?
Sorry, what?
What about side effects?
Side effects?
Yeah.
Collecting traces does not care about side effects, right?
Right.
Yeah. So we just execute all those methods, and whatever it's done to the server state does not matter.
And like, what order of magnitude of traces do you need for?
For us, we get like thousands of traces, but we do like need some enough coverage of the methods so that we can infer the semantic type for all the methods. If the trace does not cover some method, then we cannot infer the semantic type for it.
I'm curious about this retrospective execution, because it seems very useful not just in this scenario, but other scenarios as well, potentially, right? Can you see this being used in more general than just this case study? Because not running the programs, my experience in a lot of program synthesis in past was that there's a lot of overhead of compiling and running, right? So if you can actually have this, it could save a lot of that, even if you're just guessing, I guess.
Yeah, definitely. But I think for most cases, like we have a binary executable file, we can always execute that program without care about the effectful thing. But in our world, we do care about. And I think if you also have some similar scenario that care about that we do not always execute the program from the same state, then this technique should be applied to other domains.
Okay. Well, let's thank the speaker again. Thank you very much.